Chapter 8, Techniques of Integration. We're going to do in this chapter 4 methods for integration of function. We'll start from 8.1 until 8.4. So we'll be doing 4 methods from 8.1 until 8.4. So by end of section 4, if an integration is given to you, you will have to decide which method to use. This table is a table of antiderivatives from Calculus 1. So these are not techniques, these are only antiderivatives, just like, for example, we know that the derivative of sine is cosine, integration of cosine is sine, and so on. These are all the antiderivatives. For example, integration of u prime divide u, this is ln u, and so on. You must remember these kind of things in order to proceed with the chapter. 8.1, which is method of integration by parts, this is actually like a product rule for integration. Just like we had a product rule for differentiation, this is a product rule of integration. This is the rule actually. Now it's very interesting to know that this rule comes from the product rule for differentiation, which is this. Derivative of uv is uv prime plus u prime v, and so on. If you integrate both sides, so the integration of the derivative is uv, and this is integration of these, you are going to, and if you keep this in one side and transfer this here, you are going to end up with the integration by part rule. Now it will be easy to think of this rule in the table form. This is how I'm going to use it later on. You can think about it this way. You see, we are going to use this rule to integrate functions like this, which are a product. So one of them we are going to take it as u, the other one we are going to take it as dv. We'll differentiate and integrate. This is how we are going to use this rule. So instead of memorizing this, you can just think about it this way. This is the rule: uv minus integration of dv minus integration of v du. So if you look at it again, really, you have integration of u dv, which is this, equal to uv, which is this, and minus integration of v du, which is this. So it's easy to think of the rule this way, which is the table form. This is how I'm going to use it when I start solving some examples. Now let us look at some exercises for the integration by part. Now, this is the first one. We have product of two functions here, exponential and polynomial function, which is x. Now, you see, the main thing about integration by part is what to choose for u and what to choose for dv. For example, here, if I choose, this is u, this is dv, and I'm going to differentiate and integrate. That's the rule. If I choose for u e to the power 3x, which is the wrong choice really, but let us see what happened. And this is x dx. Dx should be always here because we are going to integrate, so we need a dx for integration. Integration is this, and differentiation is a 3e3x dx. Now this is the rule, this minus integration of that. Now if you look at the integration, which is the main thing here, it should get more easy, but actually this is integration of x squared e3x, which is worse than this, more difficult than this, because that was x e3x, while this integration now is x squared e3x, which means that was the wrong choice. So it's very important when we choose u and dv, this integration should be more easier than the first one. So let us see the right choice here, the correct one. So now let us repeat this exercise, but using the correct choice for u. So u has to be taken as x, and dv has to be taken as e3x dx. So du is 1 dx, and v is equal third e3x. This is the rule, uv minus integration of v du. So integration of x e3x, this is the required integration, is equal uv, which is third x e3x, which is this one, minus integration of v du, which is this here, this is there, e3x dx. This is equal to 3. You see now this integration is much easier than the first one, and it should become easier. If it becomes more difficult, that means we have taken the wrong choice. This is integration of third e3x is 1 over 9, because integration of e3x is third again, e3x plus c. Now from this exercise we have learned that when we have a polynomial like x or x squared with an exponential, the polynomial has to be taken as u, and dv has to be the exponential. Now we have seen from this exercise that if we had an x or x squared with exponential, then x has to be taken as u. Now what about if we have a polynomial here, it is theta, it could have which is just like if we have dx, it would be x. So it is theta and cosine or sine. What about if we had an x or x cubed here and the ln? Now what do we choose for u? Now here again we are going to take u as theta and dv as cosine pi theta d theta. So again, if we have an x with a cosine or sine, we take x as u. Here it is theta instead of x, but it is basically just the same thing. Du is equal to 1 d theta, v is equal to sine pi theta divided by pi. Now that's the rule, uv minus integration of v du. So integration of, we don't need to write it, it will just take space really. So this integration now is equal to uv, which is 1 divided pi theta sine pi theta, which is this, minus integration of 1 over pi, can be kept out, which is this, sine pi theta d theta. So this times this, minus integration. This integration of course is much easier than the first one. So this is 1 divided pi theta sine pi theta minus 1 pi square cosine, because it's going to be cosine pi theta divide pi, so this will be pi square, and it should be minus, so this will become a plus constant. So what do we learn from this exercise? We have learned that if we have a polynomial like x or theta here times a sine or cosine, u has to be taken as the polynomial like x or theta or x squared, and sine and cosine has to be taken as d. Number 6. Now here we have polynomial which is x power 3 times ln x. Here in number 8, when we had a polynomial times exponential, we have taken u as a polynomial, which is x. And when we had theta times cosine, again polynomial times cosine, we also took u as the polynomial. Here we are going to take, let's erase this first, because we are going to need the space. We are going to do this exercise later on. Here we are going to take u not as x like before, we are going to take it as ln x, because if we take dv as ln x here, if we take that will be, it's difficult to integrate ln x, so we have to take dv as x cubed dx. So du is 1 divided x dx. So dv here cannot be taken as ln x, because you cannot integrate ln x. Anyway, ln x can be integrated only by parts, as we are going to see later on. So whenever we have ln with an x, then ln has to be taken as u. So v here is equal to x power 4 divided 4. This is the rule, uv minus. So integration from 1 to e x cubed ln x is equal to x to the power 4 divide 4 ln x from 1 to e, this is definite integration, minus integration from 1 to e for x4 divide 4 times 1 divide x dx. Let's erase this now. Now, this is equal. Let's finish the integration and then we are going to do the substitution. This is 1 to e, this is minus, quarter is out. This cancel with this, so this is x cubed. Integration of x cubed is x4 divided by 4 from 1 to e. Now start substituting e, the upper limit, e4 divide 4 ln e minus 1 to the power 4 divide 4 ln 1 minus, this quarter is out, so it will be minus 1 over 16, and it is e to the power 4 minus 1 to the power of 4. Then this is equal to e to the power 4 divide 4 ln e, which is 1, minus ln 1 is 0. So we are going to have here minus 1 divide 16 e to the power 4, which is this, and plus 1 divide 16, multiply this by that. So this is equal, if you multiply, you can combine the fraction. If you multiply 4 and 4 here, this is going to be 3 e to the power 4 divided by 16 plus 1 divided by 16, which can be done by calculator. Number 14, we have an x times secant square. Now, secant square is a big function, but it is easy to integrate. So, we are going to take it here as dv. This is 2x dx, and u can be taken as 4x. du is equal to 4 dx, and v is equal 10 2x divided by 2. Let's erase this. So it is 1 divided 2, 10 2x. Now this minus integration of that. So this integration now is equal to uv, which is 4x times 1 divided 2, 10 2x, minus integration of 4 times 1 divided 2, 10 2x dx. So 10 2x, we have to squeeze it dx. This is equal to 2x 10 2x minus 2 integration of 10 2x. Integration of 10 is sine divided cosine, minus 2 sine, this is sine divide cosine 2x. And so this is actually derivative of this. So it's a ln, but you need here a minus, here you need a minus here, and the 2 which are actually here. So this is equal to 2x 10 2x plus ln cosine 2x plus constant. Now if we look at number 4, this is now x square sine. We have done previously x sine or x cosine, which is integration by parts, where u is x, here u is x square, and dv is sine x dx. Now du is equal to x dx, v is equal minus cosine x, and this is the rule, which is uv. So integration of x square sine x will be equal to minus x square cosine x, which is uv, minus v du, so it's going to be plus 2x cosine x dx. But this is again product rule, so it has to be done again by part. It's integration by part. So we have to do this by part. We have to take u as 2x and dv. So this is we have to repeat by part because we had x squared. But I'm going to show you later on how to do this using the table form. This is equal to sine x and du is equal to 2 dx. Now let us see. So this now is equal to minus x squared cosine x. This integration now is equal to uv minus b du. So it's equal to plus 2x sine x minus integration of 2 sine x dx, which is equal to minus x squared cosine x plus 2x sine x minus 2. Integration of sine is minus cosine, so this will become a plus cosine x plus c. So now we have learned from this example that if we have x squared or x cubed times sine or times e also, then we have to repeat integration by part. Here we have power 2, so it will be repeated twice. If we have power 3, it will be repeated 3 times. But later on, we are going to see how to do this in a table form in a much easier way than this. Especially for higher power. For a power 2 is no problem. Now we have seen here in number 4 and number 10, whenever we have x squared or x to the power cube, sine and exponential, you see here we have x squared, we had to do this using integration by part twice or more according to the power of x. Now, for exponential and sine or exponential and cosine, we must also use integration by part twice, as we are going to see now. And it does not matter what we take for u. We take a sine or we take an e. I will have to do integration by part twice. Let us see this. Now, du is equal to cosine theta and b is equal to e theta. This minus this. So integration of e theta sine theta d theta is equal to e theta sine theta, which is uv, minus integration of e theta cosine theta. So we have ended up with the integration, which is similar to this, but instead of sine it is cosine. So it has to be done by part also. So it has to be done by parts. So here we have to take u. Now here it's very important that we take u similar to this. For example, if we have taken u here as sine, we must continue taking u as the trigonometry, which is cosine. If we have taken u here as e, we must continue taking u as e as well. So otherwise we'll end up with the wrong answer. You can try this and see if you take e here, you are going to reach like a dead end really. You will end up with a 0 equal to 0. Anyway, du is equal to minus sine theta and b is equal e theta. So now this is equal to e theta sine theta minus the integration, which is here, this uv minus b du, which is going to be minus e theta cosine theta. There is a minus here, so it will be a plus, and this is a minus, and there is a minus there also. So this will be minus integration of e theta sine theta d theta. Now this is very interesting because we are getting again an integration of exponential and trigonometry, but it is similar to this integration. So it will come this side and it will be plus. So this is minus So if it comes to the other side, it will be plus. So we are going to have 2 e to the power theta sine theta d theta is equal to e theta sine minus e theta cosine. So the required integration, which is e theta sine theta d theta, is 1 divided 2 e theta sine theta minus e theta. So I'm going to divide this by 2 cosine theta plus constant. So whenever we have exponential with sine and cosine, it has to be done using integration by part twice. You could take u as sine, which is a trigonometric function. You must continue taking u as a trigonometric function. If you have started by taking u as exponential, you must continue. If you take sine here and exponential here, and instead of minus here is going to be plus. So if you take it this side, it will be minus, and you're going to end up with 0 equal to 0. Now, integration by part can also be used to integrate inverse function and ln function. Let us see how to integrate ln of x. Now, even though we have only ln of x here, but this is how we do integration. We take u as ln x and dv as 1 dx, and du is 1 over x dx, and v as integration of 1, which is x. So uv, that's why when we had x ln x or x cubed ln x in the previous exercise, we could not take dv as ln x, because ln x itself can be done by integration, by part. Anyway, so integration of ln x is equal to uv, so x ln x, let's erase this, by, so uv minus v du, so minus integration of this, which is this. So it's x ln x minus integration of 1, which is x plus c. So this is a very famous example on integration by part, which is integration of ln x, even though we had no product here like we had in the previous exercise, but it can only be done using integration by part. Number 12, integration of sine inverse y. The integration by parts can also be used to integrate the inverse function like sine or cosine inverse or tan inverse. Again, here we don't have a product, but we have to take u as sine inverse y and dv as 1 dy. du is 1 divide root of 1 minus y squared, and v is equal to y. This is dy. So that's the rule, uv minus integration of that. So integration of sine inverse y dy is equal to uv, which is y, sine inverse y, which is this, minus integration of y divide root of 1 minus y squared dy. Now, this is equal y sine inverse y minus, we have to look at this like this is now y times 1 minus y squared to the power minus half dy. This is equal to y sine inverse y minus, this is now like u times, this is u prime, but we need a minus 2, so we have to divide by 2, and there is a minus here. So it's going to be a plus half 1 minus y squared to the power minus half plus 1, which is half, divide by half, plus c. This is cancelled with this, so we are going to have y sine inverse y plus root of 1 minus y squared plus constant. We have learned from these two examples that if we have sine inverse or length, they have to be taken as u. Tabular integration by parts. This is a short way for doing repeated integration by part when you have a polynomial times exponential or a polynomial times sine and cosine. We have done this example, which is integration in the previous exercises, which is integration by part twice. And instead of doing two steps, two separate tables, this can be done very easily in the following tabular form. This is u, this is dv. And you have to so you are putting the two tables in one table. This is the called tabular form. Now, like we have said before, that when you have a polynomial and exponential, the polynomial has to be u. So u is x squared. Differentiate until you get a 0, and it will become a 0 because it's a polynomial. And ex as dv, keep integrating until you reach the 0 level. Now, this should be plus minus like this, and you have to cross product. So your answer, which is integration of x squared ex, is going to be x squared ex, which is this, then minus this times this, which is minus 2x ex, and plus 2ex plus c. This is another example, which is again integration by part twice. This is u, this is dv, x squared, differentiate until it becomes a 0, the sign integrate, and then same thing, cross product until you come to the 0. So this is going to be equal to x squared cosine x, which is a plus this, then minus 2x times minus, so this will be plus 2x sine x, and plus 2 times this, which is minus, so minus 2 cosine x, plus constant. Now this is another example. This is x power 5 times sine x, which is 5 times integration by part. So let us do this table here. This is u, this is dv, and this is the sine. Let us change the color. Now, so we have x5, derivative is 5, x4, and 20 x cubed. Let us write this again. This is now, this is x4, this is x cubed, and this is 60 x squared. We have to squeeze it because the space is not enough. 120x, this is 120, and then 0. dv, which is sine x, this is minus cosine x, this is minus sine x, and this is cosine x, and sine x, minus cosine x, and minus sine x, plus, minus, plus, minus, this is always a plus, minus, plus, and it should be like this. Again, you have to cross product, and cross product like this, and like that, and like this. So if you look at the answer here, the first one, which is this is minus x5 cosine x. Then the second one, which is this one is minus 5 sine. There is minus here, so it is a plus 5 x4. And then this one, which is plus 20 x cubed cosine, and then this one, which is minus 60 x squared sine, and then this one, which is minus 120x cosine, and this one, there is a minus here, so plus 120 sine x plus constant. Remember, this technique only works if a polynomial function is going to be selected as u, because it will become 0 at the end. This is a 0. It's very important to remember that you cannot use it when you have x cubed with ln x. Because when you have x cubed with ln x, we don't take u as x cubed, we take u as ln x. So this method is used only if we are going to take u as x to the power, because when we differentiate it will become 0 at the end. But here when we have x cubed with ln, we take u as ln, so we cannot use tabular form. Now, as a conclusion to the chapter, let us see these key concepts. Now, you see, the main thing about this section, which is integration by parts, is what do we take for u and what do we take for dv. So which function do we choose for u and which function do we choose for dv? Anyway, let's read the following. The u has to be taken the one which is easy to differentiate, because we are going to find du. You see, this is u dv. We differentiate and integrate. So we have to choose u, the one which is easy to differentiate, and dv, the one which is easy to integrate. This is one thing. And then very important thing is, you see, you are integrating this, which is u dv. It's very important, this is the rule now, uv minus integration of dv. It's very important that this integration becomes more easier than the original one. If this integration becomes more complicated than this one, then you must, then you know that the choice here, you have done the wrong choice. Sometimes it is necessary to integrate by parts more than once. We have seen that. We have seen that when you have exponential and sine and cosine, it has to be done using integration by part twice. We have seen that if we had integration of x to the power n times e times cosine and sine, then it has to be done also using integration by part more than one time. And this, when you have a polynomial, has to be x to the power. You can even have x cubed, for example, plus x plus 1 times e to the power x dx. This is again a polynomial which has to be done by parts 3 times. It will be done using the tabular form. So whenever we have a polynomial, not necessarily only x, any polynomial times e times sine and cosine, it has to be done using the tabular form, which we did in this section. Now, last thing, which is the main thing, is the AL-mannai rule for choosing u. Now, we have seen how to choose u. We have seen that we had x to the power, we had e to the power, sine and cosine, and we had ln, and we had an inverse function, and so on. We have seen what to choose for u when this comes together, or when this comes together, or when this comes together, for example. Anyway, the AL-mannai rule, it tells you what to choose, how to choose u. Any function which comes before the other one in this list, it should be taken for u. Which means that if you have the inverse function and x to the power, now since in the integration, if you had the inverse and x to the power, for example, if you had x squared sine inverse, now inverse comes before x to the power in this list, in the AL-mannai, so the inverse has to be taken as u. So any function comes first, it has to be taken as u. So if you had, for example, a logarithmic function and x to the power, logarithmic functions comes before x, so the log has to be taken as u. And if we had x to the power and sine, as we have seen, x to the power comes before sine and tan, so x has to be taken as u. If you had x and e, then x comes before e, so it has to be taken as u, and so on. So whatever comes in the list, in this list, before the other one, it has to be taken as u, which means whatever comes first in this list, it has to be taken as u. The AL-mannai, this is inverse, logarithms, algebraic, trigonometry, exponential function. So that's give you also a kind of headlines for choosing u. Now this is last thing, integration by parts can be also used with definite integration. When you have a to b, you just have to put a to b here and a to b there.